Yesterday at King's, I got as far as this last slide of 8.2, which has this iconic image of a surface, an orientable surface, whose boundary is a knot, a trefoil knot, in fact. You can see it's a trefoil knot if you just stare at it as it's there. There are too many crossings for the usual diagram, but if we just take this edge here and sort of push this edge up right over the top, and then has to go down and join where it was before. So there's a new crossing here, but I've eliminated this crossing that was on the left and all the sort of triple crossing in the middle. And the surface has to be pulled upwards, but that would leave 3 crossings of the boundary if you stare at it, which go over, under, over. So that is indeed the trefoil knot. And it's a good sort of introduction to what I'm going to talk about in the last segment, in which we're going to talk about constructing orientable surfaces which bound a given knot. That means their boundary is that knot. And it's important for this that we want orientable surfaces. So the study will focus eventually on orientable surfaces, although you can also get non-orientable surfaces bounding knots. So let me make a start on that now. So what I'm going to do, first of all, I'm going to give you a sort of naive construction in which it doesn't guarantee orientability. In fact, most of the time it will give you non-orientable surfaces, which is interesting, but not quite what I want. So we start with the knot diagram. The construction depends upon the diagram rather than the knot itself. And as usual, let small c be the number of crossings. And let's give our diagram a chessboarding. So we have alternate white and black regions. Normally the outside is white, and that obviously makes it easier to show you. And so we can actually manufacture a surface from this in the following way. So if you look at, say, the left-hand side, what you do is where there's a crossing, which as it stands is really just a vertex, you pretend that there's really a sort of piece of cloth that's twisted. You think of the black regions as forming a piece of cloth, and it's not actually joined at the crossings. The cloth is just twisted according to the over and under passes. So I can show you that with an old bow tie I haven't worn, probably only worn once in my life. So here we have, it's meant to be black, but the black one didn't work. So the idea is that we have this sort of piece of cloth and we want to make a crossing. So we just do a half twist according to the way the crossing appears in the diagram. You can either twist one way or the other way. You follow what is done on the diagram. So you make that twist and you see that you sort of get a piece of cloth which just sort of passes through a vertex at my finger, but really I'm hiding underneath the fact that it's a connected piece of cloth. So you can imagine that at each crossing there's a sort of finite rectangle, if you like, of cloth hidden underneath, and that will give you a surface, and it may or may not be orientable. So here are 2 examples in which the knot is the trefoil knot. So on the left is the usual picture of the trefoil knot, chessboarded. On the right is a picture we've also seen. In fact, right in my introductory lecture, this was a picture which would have come out of the discussion of Mobius bound with 3 half twists. You can think of the image on the right as corresponding to the same knot in which I've chessboarded the outside. I've chessboarded with the outside black, because if you look at it, you see, if you think of the knot as not in the plane but really is in the 2 sphere, then the region on the outside would be finite, and you can swap things over. So you see on the right-hand side, the outside region just has, essentially, it just has two sort of sub-arcs here around the outside, one here and one there. So the outside region is just really a 2-gon, and you can think of it as corresponding to one of these regions here on the left-hand side. So things are swapped over, whereas the 2 black regions on the right hand side, these correspond to triangles curved triangles which would correspond to these two regions. So it's just a sort of swap over, if you like. But if we apply the same construction to the diagram on the right, it turns out that the surface will then be oriented. So why is that? Well, you see, it's like the previous example. To understand why that previous image on the previous slide was orientable, you have to you have to ask yourself, when you think of this as a cloth surface, are there two sides? When you think of it in R3 as a cloth surface, are there two sides? Is there a well-defined notion of sort of up and down, top and bottom side? And there is on the right, but not on the left. And one way of understanding that is to say, well, let's do the one on the left. You see, I could think of this as the top side. Let's put a plus to say it's sort of the top side. But after my twist, whichever way it is, it's a half twist. So this would be the underneath of the cloth. And then this would be the upside of the cloth again. But then there's a contradiction, because I can't have... there's a contradiction here, because you'd have to swap signs every time you have a crossing. Whereas on the right-hand side, there's no contradiction. I can make this the upper half of the surface. Then with all my twists, whichever way I go through, this will be the under half of the surface, and that's completely consistent. So this one is oriented, and this one is not oriented. Now, we can also compute the Euler characteristic of the surfaces quite easily. One essentially just counts... When you compute the Euler characteristic, you can actually just pretend that each crossing is a vertex. So if you do that, you can count the edges. Of course, if there are C crossings, the number of edges of the graph, that's the sort of what I call the subarcs, there would be 2C of those edges. There would be C vertices. So the Euler characteristic would be sort of C minus 2C, and then how many regions do we have? Well, let's just call it F for faces, and it's the number of black regions. So the formula for the Euler characteristic is just F minus C. And if we apply that formula on the left-hand side, you'll see that we have 3 minus 3. Of course, both diagrams have 3 crossings. So the answer would be 0. So here the Euler characteristic is 0. And here the Euler characteristic would be 2, only 2 regions, 2 black regions, minus 3 crossings, so that's minus 1. On the other hand, these surfaces both have a single boundary component, so they both have r is equal to 1. So that means that the first surface, being non-orientable, has to be the projective plane minus a disk. So actually the surface is just the Mobius band. So this is just, the surface is just the Mobius band. Whereas on the right-hand side, what we have is orientable, Euler characteristic minus 1, 1 boundary component. So this has to be the torus minus, and this was the projective plane, if you like, minus a disk. Open disk removed, and this is the torus minus an open disk. So in a sense, the right hand one is better for us because it gives an orientable, arguably it's better because it gives an orientable surface. Okay? Although, bear in mind, both surfaces are embedded in space. Once you remove disk, you can embed non-orientable. Once you remove at least one disk, you can embed any non-orientable surface in R3. So I'm just going to summarize that on the next slide, what I've just done. So as you say, the Euler characteristic on the left is 0, the one on the right is minus 1. So the one on the right, the black cloth surface with these sort of twists at each crossing to reflect the crossing itself, that will be an orientable surface, and its boundary will be the knot with the given crossings. That's the point. That's why I'm reflecting the way the crossings are under or overpass must be reflected by the twist to make sure that the boundary of our surface, of our black cloth surface, is the knot I started with before I chessboarded it. Okay, so that's a naive construction, but it's quite a useful way of seeing how surfaces can be constructed from knots. The problem is that often this gives rise to non-orientable surfaces. And in fact, if you take the if you take the next, what's the next knot in the table? It's the figure 8 knot denoted 4-1. If you take this knot and you chessboard it, or using black or white, as I explained before, do a different diagram in which you correspondingly sort of taking a different chessboarding, it will always be, the resulting surface will always be non-orientable. Okay, so I mean, I can show you just this this diagram. So with one chessboarding, with the natural chessboarding, there's the figure 8 knot with its obvious chessboarding, and there are three. You see, there are three regions, three black regions. There are 4 crossings. So if you do the calculation, it would be, what would it be? Three crossings, 3 black regions minus 4 crossings. That's -1. Well, that's all right. So that doesn't really prove anything, does it? Because that just tells you that either we've got a torus minus a disk or a Klein-Bottle minus a disk. But if we do our trick with the plus, minus, plus, we're in trouble again here. So it's definitely non-orientable. So this has to be a Klein-Bottle minus a disk, actually. And you can't get another diagram with 4 crossings would give the same result. But there is a remarkable theorem. It's not difficult really, because I'm going to give you a construction for it. Any knot is actually the boundary, so including the figure 8 knot, is the boundary of some orientable surface. And this is carried out by means of a quite simple algorithm, which I'm going to explain with a picture on the next slide. So it's perhaps hard to understand the text, but let me just tell you, and then I'll show it in action on the next slide for the figure 8 knot. So you choose a diagram for the knot where we have the figure 8 knot here. You orient it. The result won't depend upon the orientation as usual for knots, would for links. Could also apply this for links. But we orient it. We choose an orientation for the knot and follow that through as usual, so that at each crossing we know whether it's what sort of crossing it is. In fact, in this case, if we follow this round, it goes like that. It's actually the rise at each crossing. Well, the rise at this top crossing is -1, as it happens. The total rise, remember, for this standard diagram of the figure 8 knot is 0. You get 2 minuses and 2 pluses, but that's not completely relevant for what I'm doing. Anyway, the idea is that you then split the crossings in the sort of Kaufman sense. But when you do it with Kaufman, you can choose any splittings you want, and you need to sum over all splittings in theory to compute the Kaufman bracket. But that didn't require orientations. But now we have an orientation. There's only sort of one natural way of splitting each crossing compatible with the orientation, and that's precisely what we did when we applied this Skine relationship for the Jones polynomial. So I'm going to explain that on the next page. But you see, with the orientation, you want to do the splittings consistent with the orientation. So if you do that at each crossing, you'll eliminate all the crossings. So you'll just be left with unknots, because there are no crossings. You'll be left with a diagram with a number of circles. When I say circles, I mean topological circle, topologically homeomorphic to circles. And they'll be unknots because they're in the plane. And each of those unknots, you can think of it as the boundary, because it's in the plane. You can think of it as the boundary of a disk. And then you have these separate disks, but we want a connected surface. So then it's a bit like what we did before. We sort of paste in twisted bands in place of the crossings. And I won't say more on this page, but the key thing that will give you an orientable surface. Let me show you this then in action. Okay, so there's you can't quite see it because it's in yellow, but there is the standard diagram of the figure 8 knot underlying what I've drawn, and I've chosen the same orientation as before. So I've chosen this orientation here. You should really carry the arrows through and see what's happening at every crossing. So we're going round here. So I'm following the knot. Follow the knot round, not the curves I've drawn. So that arrow will go up, that arrow will go up there. The red ones correspond to the underlying knot diagram. and then it's going this way and it's going down here. So if you look at this crossing here, you see that in order to split that, compatible with the orientation, I can't take this strand up here, because then the other one would have to cross through it, and I want to eliminate the crossing. I want to split it. So I've got no choice really but to split it this way. And this one has to be split this way. And this one has to be split this way. And this one has to be split that way. So I do those splittings. That allows me to carry the orientations on all of the loops that remain. And I essentially get 3 unknots in the plane. One is nested inside, this one here is nested inside the other one. Doesn't matter, but I get 3 unknots. And these are called Seifert circles. So they're circles in the sense topologically equivalent to circles, homeomorphic to circles. They don't look like circles, but you get these unknots. As we've seen before when we're doing the Kaufman business, any knot you can split in any way you like, all the crossings, and you'll get a number of unknots at the end, and that was important, that number, in the formula for the Kaufman bracket. But this time I'm using an orientation, which gives me one specific splitting, or one of all the crossings. For each crossing I have a determined splitting, completely determined, so I get one state in the language of the Kaufman bracket. So then how do I construct the surface? Well, for each point that was a crossing, I have to so first of all, I think of filling in these circles. See, any closed circle in the plane bounds a disk, that's the theorem. I fill in these circles. Now, unfortunately, if one's nested in the other, I have to sort of raise it up. I have to imagine that it's sitting vertically above the other one. So I fill in the one underneath, if you like, and then the smaller one is sort of vertically above the disk. These are disks topologically, homeomorphic to disks. And then I fill in the one above it and think of it as a bit higher. But that would give me 3 disconnected disks. I want to then make the whole thing connected to get a surface, and I want it to be orientable. So what I do is, for each crossing, I put in, if you like, a small rectangle or ribbon that reflects the actual crossing. So here, this was the overpass. So for the top left crossing, I'm going to put in a sort of twisted ribbon whose boundary looks like this, and I can join that to the disks, if you like. If I've already got some vertices, doesn't matter. And this is the ribbon. This is the twisted ribbon, just like my tie here. I've just twisted it and put it in, but the twist has to reflect the nature of the crossing. Whether it's over or under gives you have to do the twist in the correct way, because you want a surface whose boundary is the original knot. So I must reflect the crossings. So if it's not an alternating knot, for example, I'll have 2 adjacent. I've got to reflect the nature of the crossing. So I put those discs in, these twisted bands, they're called, in. So these are sort of inserted in place of all the crossings. That can be done. And then if you think about it, it's going to be oriented. Because why is it oriented? Because each disc has a natural orientation. Because we did the splittings in the correct way, compatible with the orientation, each disc has a natural orientation. So the top disc, we have this sort of, in the plane, this anti-clockwise orientation. And the bottom 2 discs, both the big one and the little one, have a clockwise orientation. They acquire an orientation, and when you put your twisted bands in, you'll see that they will be put in consistent with the orientation. So because these two discs are sort of disjoint, that one is outside the other, that means the orientation reverses with this twisted band. But if one is nested in the other, you can only get the orientations to agree, again, with the twisted band. If you put an ordinary band in, the orientations would flip over. Now, you need to think about that, maybe do some paper models, and you'll see that the surface is orientable, just as the one on the last slide of 8.2 was in fact orientable. Not completely obvious, but if you look at it, it is. So that is the algorithm. And what you get in this particular case, well, we're going to have three. I'm going to show you just now. We're going to have three discs. One is going to be raised up a bit because it corresponds to this inner disc, and we're going to have a total of 4 twisted bands. Okay, so it looks like this. So we see our 3 discs. The picture slightly the wrong way around because this is the top one. Here we have the top of the yellow diagram here. And here's the bottom bit in which you see. Notice what I meant with this orientation. So these two, you can think of the sort of dark blue as corresponding to my clockwise orientation. So in order to keep the surfaces sort of the same side, I need this twisted band, because if the band's not twisted, it would pass from the top of the disc on the top to the bottom of the disc below, and that would be the wrong way around. But everything in this picture is consistent. And the diagram you get, because of the construction, the boundary we get, which has been emphasized here, it's just a curve, not a tube, the boundary of this surface is ambient isotopic to the figure 8 knot. So here this is construction, quite elementary really, of an orientable surface whose boundary is any given knot. And that's called Seifert's algorithm. Okay, you can do fancier things with the same surface actually, but the most important thing to tell you next is that you can easily compute the Euler characteristic of the surface you get. Because what happens is, basically, I mean, I did this calculation right for the image right at the start of today. I did it on campus, but I didn't have to be quite as detailed as I did it. I put in extra vertices and extra edges and so on. But you can actually, if you think for a moment, you can see that what happens, the formula is going to be very simple. Each disk sort of contributes +1 to the Euler characteristic, and each ribbon you add contributes -1. And then you've got to remember there's one boundary component. So the Euler characteristic with one boundary component of an orientable surface with one boundary component is 2g, 2 minus 2g minus 1, -1 for the boundary component. And so this has got to equal the number of disks, which is the number of Seifert surfaces, minus the number of crossings. And so you solve for g and you get this formula for g. So if we do that for the figure 8 knot, what are we going to get? We're going to get 1/2, the number of crossings is 4, the number of Seifert circles is 3, plus 1. That's equal to, it's half the genus. That's equal to 5 minus 3, that's a -2. It's got to be an even number inside the parenthesis. Sorry, plus 2. The genus is equal to 1. Okay, so that means genus 1. It means we've got a torus. We started with a torus and we just removed a disk. So you can't see that. Anyway, so it's 4 minus 3 plus 1. So there's a missing +1. You get an answer of 1. Put the -1 there. Sorry here. So the boundary, the surface I just showed you, and here are 2 other models of it. These are a bit fancy. I'm not expecting you to draw these, but the surface has genus 1, which means that it is the torus minus a disk. The boundary of the disk, of course, is homeomorphic to a circle, but with the surface embedded this way in space, which is what we're talking about, the boundary becomes ambient isotopic to the figure 8 knot. In this diagram on the left, it's very similar to the previous one, except I've sort of shrunk the one of the discs down. So one of the dark blue discs you saw in the previous diagram has sort of been shrunk down into this sort of, so instead of having a twisted ribbon half twist, we've got 3 half twists on the left hand side to make up for the missing disc. It's not quite so easy to understand how you get the rather more elegant form on the right. You can think of sort of soap bubbles at this point, but the important thing is there are no self-intersections. Often if you use dip wires in soap. You can have a wire frame which represents the figure 8 knot, but typically if you dip it in soapy water, you'll get sort of self-intersections. The soap film will form in self-intersections. But if there are no self-intersections, then we'll have an orientable surface, not necessarily one produced by this algorithm, but we'll have an orientable surface which bounds the the wire frame you put in the soapy water. Okay. So let me give, this is the last slide, we can now define the genus of any knot. So the genus of a knot is the least genus of an orientable surface whose boundary is that knot. And so by the definition, because we're taking the least overall conceivable orientable surfaces, it's an invariant of the knot, but it's often not easy to compute. So I've given you an algorithm that produces such a surface, but that doesn't necessarily produce the surface of least genus. There may be another surface of lower genus that bounds the same knot. However, if the knot diagram was alternating, then I think it always works that the Seifert algorithm does give a surface of least genus. So the genus of that Seifert surface, as it's called, would be the genus of the knot. So I think it's fair to say that for almost all knots you're going to meet the genus. It's not a theorem, but in practice, the genus of the Seifert surface will be the genus of the knot. It also follows that if the genus is 0, that means that K, but the genus of the, in the classification of the orientable surface, the surface would have to be a sphere minus a disk, which is itself a disk. So in that case, the knot bounds a disk, and that means that it has to be the unknot, because you can sort of shrink it in, and it's ambient isotropic to the unknot. Well, now I can come back to the image we started with. In fact, this is the Seifert surface of the trefoil knot of the formed from the usual diagram of the trefoil knot. So you see what the usual diagram, because basically what goes on is we have our 3 discs. So we have our 2 discs. Sorry, the one we saw at the beginning. We have our 2 discs joined. The diagram I showed you at the beginning on the right, we have our, sorry, no, let's start again. We have the trefoil knot. Let me try and do all this. We have a trefoil knot. Let's just draw the standard diagram of the trefoil knot. When you orient it, you'll find that there are 2, you'll find that you'll just get 2 Seifert circles. One will be embedded in the other one. So you'll sort of just get 2 Seifert circles like this to deformation. So we're in that situation. So we have 2 discs. So I put one on top of the other. They're both the same color because the orientations will match up both clockwise. And then we put in these twisted, for the 3 crossings which we eliminated here, here and here, we put in these twisted bands and everything matches up. So that is in fact that previous image I showed you also yesterday is the image, this is the Seifert surface corresponding to the trefoil knot. Okay, so and that also bounds, that corresponds to a torus. You can compute the Euler characteristic again. In this case, what is the formula? Let's just finish with that. So in this case, the formula is 1/2, the genus is 1/2 into the number of the Seifert surfaces. I'll remind myself of the formula here. 1/2 into C minus S plus 1. So 1/2 into C, which is the number of crossings, minus the number of circles, plus 1. So that's, again, 4 minus 2, 1/2 of 2 is equal to 1. So the genus is 1, which again tells you that we're dealing with the torus minus the disk. And many of the sort of simpler knots will have genus 1, and they can be filled in basically by a torus in which the knot is corresponds to the boundary of the disk. But to actually pass from these images here to seeing a sort of torus with a little disk removed, that's harder to imagine the transformation, the homeomorphism, but it always exists.